Hello and welcome to this course on quantum computation, which will mostly be done by me, Dr. James Wotton of IBM Quantum. The videos in this lecture will follow sections from the Qiskit textbook, and this first video, which is part 1 of lecture 1, will follow the atoms of computation. The videos in this course will not just be me reading out sections from the Qiskit textbook, but will instead be whiteboard presentations which follow the same content but in a bit of a different way, and therefore hopefully help you to better understand what's going on. And given that they're whiteboard presentations, I mostly won't be looking into the camera like this, but I'll be looking at the whiteboard like that. So I'm not ignoring you, I'm just looking at the whiteboard. Okay, so where do you begin a course on quantum computation? Well, a lot of people begin by writing down an equation such as the one that I'm writing here. They might even say that it is simple, a simple example of quantum superposition. And that does seem like a kind of good place to start, because superposition is a very key concept in quantum physics in general and also in quantum computation. But there's a lot of complexity in this equation. The notation's probably the worst thing. What are these strange vertical lines? We have these things that look like greater than signs, but they're not greater than signs. We have the familiar concept of addition. However, what are these strange objects that we are adding? There's some Greek to look fancy, of course. In fact, the equal sign is probably the only thing here that's not controversial. So I don't think this is a great place to start a course on quantum computation. So let's not start here. Let's start somewhere else. Well, of course I did just start here, but only to complain about it. Instead, this lecture is about breaking down quantum computing into its most fundamental parts, and we can start this at the most abstract level. What is quantum computing? Well, it is quantum and computing. So here, quantum is quantum physics. If you have a physics background, you will probably know about quantum. And computing is computer science. If you have a background in computer science, if you have a degree in computer science, you will know far more about computer science than you need for this course. Whichever of these two backgrounds you're from, you will need to learn something about the other in order to fully understand quantum computing, but you'll also need to re-understand something about your own background. If you're from a physics background, you've probably done exercises where you were given some sort of potential well, and you were told that there is a quantum particle living in that well, and you were asked to solve the Schrödinger equation to find out what wave functions are eigenstates of that potential well. So this is a continuous variable system. The particle can be anywhere in a continuum of points within the potential well. You have to solve a differential equation to find these wave functions. It's a very continuous approach to quantum mechanics, and it's not really the way that we think about things in terms of quantum computing. In quantum computing, our quantum system is the quantum bit. And so just as a bit has two values, 0 and 1, a quantum bit has two possible states, 0 and 1. And there's those strange greater than signs and vertical lines again. But this is just to point out that this is a discrete system. And so not like the continuous systems that exercises in a physics degree love to use. Also, the way we think about time evolution is often quite discrete as well. Rather than, again, solving a differential equation to get a continuous change over time, we often think about the time evolution in a quantum computation as being packaged up into little chunks, which we build as if we're playing with Lego. So because of these things, if you're coming at this from a physics background, you're going to have to rethink your quantum physics a bit in order to learn the new language, the new way of thinking that we do in quantum computing. If you come from a computer science background or a programming background, you're also going to need to rethink things a bit. And let's just think of the programming aspect for this for now. When we do programming, we're often used to thinking at quite a high level of abstraction. If you ask someone, what is the simplest thing that can be done in programming, they might say something like adding a couple of numbers. But even for such a simple operation as adding, there are technicalities, depending on whether you're adding integers or floats, whether you're combining different types of numbers, whether they're signed or unsigned. there's going to be all kinds of different stuff going on at the level of the bits, which is where this information is actually encoded. When you look at the bits, there are things that need to be taken care of in order to implement an algorithm for adding. It's not something that's complicated, it's something you could easily explain to a primary school child, but still it needs to be done. And so that is more reflective of what is the simplest thing we can do in programming than the higher level abstract operation of addition itself. So now, in our quest to break down quantum computing into its simplest parts, let's look at this simple part of programming. Let's look at how you can actually add. And for that, we have to go back to primary school. So how do we add? Well, let's start with a number. So let's do 7,214 with 1,821. These are fairly arbitrary numbers that I've chosen, so don't read too much into them. And what I'm going to do is go down the columns and add pairs of single digit numbers. So first I add the 4 and the 1. And what does that give me? Well, 5, of course. And then 1 add 2, it will not surprise you to learn, is 3. Now with the next one, things get a little bit more interesting. 2 add 8 is 10. 10 is a 2-digit number, so we are going to have to do the carry operation. We keep the 0 part of 10, we carry the 1, and now in the next column we're going to have to add 3 single-digit numbers. 7 add 1 is of course 9. But still that's something we can decompose into adding pairs of single-digit numbers, because we can do the 7 add 1 is 8, and then the 8 add 1 is 9. Whichever way you do it, we get a 9, and so the answer is 9,035. The answer is not really the important part. The important part is that this operation of adding fairly large numbers was boiled down into lots of operations where we just added pairs of single-digit numbers. So adding pairs of single-digit numbers is a more fundamental operation. It is more towards our atom of computation, although it's not quite there yet. It's more like a molecule of computation. So before we continue, let's motivate a bit more why we are looking for the atoms of computation. And it is because we want to build a computer. We want to build some sort of device which will do maths for us. So we want to be able to do something like tell it 1 plus 1 and then stick that into some magical black box of computerness and then have it spit out the answer, which in this case is 2. So what does this require? It requires a physical system that we can use to encode information that will define our problem, and that physical system also needs to have some sort of interaction that we can induce, which will process the information in the way that it needs to do in order to give us the solution of our problem. So now that we know that addition is composed of lots of operations in which we add single-digit numbers, we can look for some sort of physical system in which we can find states which can encode those numbers and a physical interaction which can implement the process of adding single-digit numbers. And with that, we can hope to then build it in a more complicated way in order to add larger numbers and perhaps even do more complicated mathematics. But what does it mean to have a physical system that can add pairs of single-digit numbers? Well, for one thing, we need to have different physical states that it can encode the different digits. And there are 10 of these digits. 0, 1, 2. Of course, I don't need to write them all out. But as you well know, there are 10 of them. And it also means that we have to induce some sort of physical interaction that can recognize all possible pairs of digits and prepare another physical state in the sum of those. So if we prepare the input states as 0 and 1, then after we've induced this interaction, it has to give us an output state of 1. If we prepare them as 2 and 4, for example, it has to give us an output state of 6, and so on and so forth. There are many of these possible pairs of inputs that we can put in. Each of them have a specific output, and we have to make sure our interaction does all of these. And as you can imagine, that could be fairly complicated in general. We are giving ourselves a lot of work to do just because we're using base 10, because we are representing our numbers using base 10. If we represent our numbers using base 2 instead, then things are going to be simpler. It will mean that we need more digits in order to represent a number, but the operations on each of these digits will be simpler. So let's, instead of looking at decimal, start looking at the simplest number system, which is binary. So I'm sure you're all familiar with the concept that we can represent numbers in different bases, but nevertheless, let's do a quick refresher. When we write down a number like 9,214, we're writing this as 9 thousands, which are 10 to the 3s, and 2 hundreds, which are 10 to the 2s, and 1 10, which is 10 to the 1, and then 4 ones, which are 10 to the 0. And there is nothing special about 10 which allows us to do this. We could indeed use any number as a base here, and if we used binary, that means we're using base 2. So we're writing it as 1 times 10 to the 13 plus, well, a bunch of other stuff. So in decimal, so using base 10, we only needed 4 digits here, but each of them was represented by one of 10 symbols from 0 to 9. If we use binary, we need 14 digits, so that's more. However, each of them is represented by a binary digit, a bit, which is only 0 or 1. Going back to addition, the addition algorithm works completely the same in binary as it did in decimal. So let's start with a number such as 1, 1, 1, 0, 0, and let's add that to 0, 1, 0, 1, 0. You can work out what these numbers are in decimal yourself if you want to have that exercise. And we can go along these columns, adding them again. So 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is also 1. And now here's where it gets fun. 1 plus 1 is 2. But 2 in binary is written, of course, as 1 times 2 to the 1 plus 0 times 2 to the 0. And so we represent it as a bit string 1, 0. So here we have the need to carry. We take the 0 and we put it there. We carry the 1, and then we have to do another 1 plus 1 in the next column, and we end up with our final answer. Here we saw everything that addition in binary has to offer. We can do 0 plus 0, 0 plus 1, 1 plus 0, and 1 plus 1. Those are the only 4 possibilities when you add 2 single bits. So this fundamental component of addition in binary is a lot simpler than the equivalent single-digit addition in decimal. Now this fundamental component of adding in binary has a name, and it's called a half adder. So let's write down the action of a half adder in a convenient table form, which is called a truth table. We're going to call the inputs A and B, so these are the 2 single bits that we're adding, and we're going to call the outputs C for carry and S for sum. Now I'm going to magically draw some straight lines. So let's fill up this table. In the case that we're adding 0 and 0, the answer is 0, because 0 plus 0 is 0. 0 plus 1 gives us 1. 1 plus 0 also gives us 1. And 1 plus 1 gives us 2, which when represented in binary is 1, 0. That's a 2-bit string. So let's pad these all out with zeros in order to make everything a 2-bit string nice and consistent. Even this simple operation is not the simplest thing there is. We can break this down into two even simpler operations, one of which takes the two inputs and computes the sum digit, and the other which takes the two inputs and produces the carry digit. And now I will magically make those appear. Through the magic of editing, I've spared you most of the table creation, but we still have to put in the outputs. For the sum digit, 0 and 0 make 0, 0 and 1 make 1, 1 and 0 make 1, and 1 and 1 make 0. So you see we have a 1 as the output in the case that either one or the other of the outputs were 1. Not in the case that neither were 1, and not in the case that both were 1. So it is an exclusive OR, and that is what we call this basic operation, the exclusive OR XOR. In the case of the carry digit, it's a 1 in only one case, and that is when A and B are both 1. And the emphasis on the and there was extremely purposeful, and is what we call this basic operation. And these basic operations are known as gates. They're known as Boolean logic gates. The reason for the word gate is not really important, but it is a word that we're going to be using a lot during this course, so it's good to get used to it. So one thing that we like to do with Boolean logic gates is represent them graphically. Typically we have our inputs on the left, and then we draw lines going from left to right, which represent their lives. And then we have them go through a strange symbol, which represents the action of the gate. For the case of an exclusive OR, it looks something like that. Consult the Qiskit textbook if you want to see what it really looks like. And then we have another line coming out and gives us our output, which in this case is S. For the case of the AND gate, we find that my trackpad didn't really want to do that A. And similarly, though, we have a symbol which represents the action of the gate, and we have lines which represent the lives of the bits going through this computation. If we move up one layer of complexity, we can do the same thing now with the half adder. Our molecule of computation can be drawn in terms of a couple of these atoms of computation, the fundamental logic gates. So we can take our inputs on the left, our A and B, and we can draw a couple of lines which show them going into an exclusive OR gate. I'll draw that in a moment. But another thing we can do is make copies of these inputs. So we draw little dots to denote we're taking a copy. So we take our B and we take our A, and then these copies can go into another gate, which is going to be our AND gate. So now all we have to do is draw the two gates. So we draw our exclusive OR as being this rather strange Federation insignia is what I think it looks like. We can draw our AND gate, and then we can take our outputs out, which I draw with a nice straight line, which only goes to highlight how poorly the gates were drawn, but nevertheless. And this is our sum digit, and this is our carry digit. So far this has been completely non-quantum, it's been completely classical. These Boolean logic gates are how we break conventional digital computing down into its fundamental components, or at least they're one of the possible models we can use to do this. But we of course are talking about quantum computing in this course, so we want to break quantum computing down to its fundamental components, and we also express that in terms of gates. So to explore the atoms of quantum computation, let's again build a half adder, but now using the language of quantum computing. So for that, we're going to need an XOR, but if you look down the list of quantum gates, you will not find anything called an XOR. What you will instead find is something called a controlled NOT or C0, and is sometimes also referred to as a CX, and in fact that's what it's referred to in Qiskit. Now again, the motivation for breaking computation down into its atoms is to help us find a physical system which we can trick into doing the maths for us. In the case of a gate, we need to find some physical system which can, by its time evolution, implement this operation, which is going to take the input and turn it into the output. When we're doing quantum computation, we're going to use a quantum system, and time evolution in quantum systems is unitary. That has some consequences that we'll look into later in the course, but for now it's sufficient to say that it means that our gates are going to have as many outputs as they are inputs, which is slightly different to the Boolean logic gates that we just looked at, which had 2 inputs and just 1 output. In our quantum gate, we again start by writing our 2 inputs on the left. These are input bits. Of course, they need to be quantum bits in general, but we'll come to complications of quantum bits in later lectures. Again, also we're going to draw their history as a line from left to right, and we are going to get 2 outputs. One is just going to be a copy of the input A, and the other is going to be the thing we actually want overwritten on top of the input B. The symbol which depicts the action of the quantum gate has a dot on one side and what is basically a circle with a plus sign on the other side and a line connecting the two. So this here is our quantum gate, and you can see that it's asymmetric. Well, the side with the dot is the one for which we just get a copy of the input, and the side with a circle and the plus sign is the one for which we overwrite with the output. This is a very simplistic way of looking at a controlled NOT, and it's also very much motivated by the fact that we're thinking in terms of Boolean logic gates in this lecture. We will learn more about the controlled NOT in later lectures, but this is sufficient to say for today. The controlled NOT is the gate which provides our exclusive OR. Okay, now for the AND gate. Again, if you look down the list of quantum gates, you will not find anything called the AND gate, but what you will hopefully find is something called the Toffoli gate. And the Toffoli gate is what is going to do the effect of the AND for us. In this case, we need 3 inputs. We have A, B, and we just have a third input, which is 0. This is because the Toffoli gate has to act on 3 qubits. Again, we draw lines from left to right representing the history of these. And in the case for our 2 inputs, the output is just going to be a copy of these 2 inputs, at least in this simple effect of making our AND. And otherwise, the symbol looks very much like that for the controlled NOT, except that it has 2 of these inputs with a dot on. So both for the Toffoli and the controlled NOT, these kinds of inputs are called the controls, and the other one is called the target. And again, in this case, it is the target that gets overwritten with our output, in this case, the carry digit. Okay, so now we have the quantum gates that can do the exclusive OR and the AND, which are our controlled NOT and our Toffoli gates. We can now compose these into a half adder. And our half adder, just to remind ourselves, is something which adds 2 single bits A and B. So of course we need our 2 single bits A and B that we're going to add. And because we're using the Toffoli, we're going to need another bit initialized in state 0. And now we can go along and put these lines which represent the lives of the bits, and they're going to go through 2 gates. The first of these 2 gates is the one that is going to compute the sum digit, and this is simply going to be the Toffoli. So let's have the Toffoli here, and this overwrites the third bit with the carry digit. But if we just think of what's going on here, we've still got our A and our B coming out as copies there. And now we can do our controlled NOT using those. And this gives us as an output our sum digit. And of course we also get a copy of one of our inputs, but we don't care about that. And there are 2 technicalities we should really look at before we can truly say that this is how we do a half adder using quantum computation. One is that these are quantum bits, and quantum bits do not have to be in a definite state of 0 and 1 at every point in the computation. In conventional digital computation, when you have these lines that represent bits, you can truly say what that bit value is at every point in the line. In a quantum computation, you can't. We only have definite values when you ask for them, when you do a process called measurement to tell a quantum bit that it has to decide on a definite 0 or 1 now because we need an output. So in order to actually have our output, we need to put in a couple of these measurement operations which will make our quantum bits take definite bit values. So let's make a little space at the end here, and that will give us enough space to insert our measurement operations. A measurement operation is denoted by a box, and inside that box we have a rudimentary picture of a measurement device. So that is a measurement operation which is just extracting a definite classical 0 or 1 from the quantum bit. Also, there's another gate that we're going to need to use. The classical version is called the NOT gate, and it is the simplest of all of the gates. This is one which takes a single bit as input, and if the single input bit is 0, it outputs a 1, and if it's 1, then the output is a 0, so it just flips the bit. And this is represented by a triangle, and this triangle also has a circle on the end. So if you see this symbol, you'll know that it's a NOT gate. In terms of quantum computing, we usually use something called an X gate in order to do the effect of a NOT gate. This is represented by a box, and in that box we join X. The way we're going to need to use the X gate in this quantum computation is to prepare our input. So let's just think of a specific example of an input. Let's say we are trying to solve the very tricky mathematical problem of what is 1 plus 1. This means that both A and B are equal to 1. So if we were looking at the case that only A was 1, we would only have to put in one of these X gates. So we would put it in here. But instead we're looking at the case where both A and B are 1. So in that case we need to flip both of these bits and put in a couple of X gates. So let's put in another one here. And here we have basically all the parts of a quantum computation. At the beginning, you initialize your input. At the end, you extract your output. And in the middle, you do your actual computation. This is what all quantum computing is made up of. When we think of a computation as being made up of basic gates like this, we call it a circuit. So our circuits are basically things where we initially initialize our input. We then drive the interaction which does our computation, and then at the end we extract it. Sometimes it gets a bit more complicated than that, but that's the basics. And now you've seen the basics of quantum computation performing one of the simplest operations in all of computation, which is the half adder. And I think that's a good place to start a course on quantum computing. In this video, we'll be looking at the section, what is quantum? To get a bit of a sense of how it might be useful to us in quantum computation. As with the atoms of computation, let's start with something you probably did in primary school, which is a very simple analysis of probabilities. The classic example of a probabilistic system is a coin, which can either be heads or tails after you flip it. So let's write an H for heads and a T for tails, and these are the two possible states after we've flipped it. But when it's resting on our finger before the flip, it also has a state. So let's write down a H for heads there. And we can assign probabilities that that initial heads becomes heads after the flip, and the probability that it becomes tails. For a fair coin, it is independent of the initial state, and it's just 50-50. We can also write one of these down for the case that it starts off tails. So let's do that. We start off tails and we go heads and we go tails after the flip, and we write down some nice lines connecting those, and we write down a couple of fair probabilities of half each. And of course, we can write down a probability tree for two flips. So we can now imagine that these two input states, heads and tails, are the inputs from an earlier flip. We can write a couple of lines connecting them to their initial state, which let's imagine is just a heads. And we can write down some probabilities for these transitions. So we have, again, for a fair coin, half here and half there. And now we've done that, we can work out the probability for this whole process of going from this initial heads via a heads to, say, a tails. The way we work this out is we look at all of the probabilities along the process, which is this half and this half, and we multiply them together. So half times half is a quarter. And if we wanted to work out the probability that it was tails at the end, independent of what happened in the middle, we would then also take into account this other possible way of getting that. So the possibility of going from heads to tails to tails. Again, in this case, we have half times half equals a quarter, and we can add these two quarters up. A quarter plus a quarter equals half. So the probability of starting with a heads, flipping the coin twice and ending up with a tails is half when you have a fair coin, which is of course what we expect, and it's nice to see maths do what we expect. The coin flip is an example of a process that obeys classical mechanics where we can't accurately predict what the outcome is going to be, and so we call it random. Let's now look at a quantum process which outputs random results, and because we're doing quantum computing, we're going to do that using a quantum circuit. First, let's start off with a classical circuit where we begin with a classical bit value, 0 or 1. We end with a classical bit value, 0 or 1, and the information passes through the circuit by means of a line. So this is the simplest classical Boolean circuit you could have. You have a 0 at the input, nothing happens to it, and it's a 0 at the output. So this is a good baseline from which we can start to represent what a quantum circuit looks like. Well, in a quantum circuit, the information is encoded in a quantum system, so it's a quantum bit or qubit. And to remind ourselves that it's a quantum bit, we put some weird notation around our 0 value. Nevertheless, our output, we still want to be a classical bit. So what we're going to do is move that down here, and we're going to have a process by which the quantum bit is turned into a classical bit that we can actually look at as humans. This process is denoted by the measurement gate, which is a box with a rudimentary little measurement device written in it. And then we're going to draw some lines coming out of that, which are going to be double lines. In quantum circuits, we use double lines to represent the passage of classical information and single lines to represent the passage of quantum information. So this is just our circuit of we have an initial 0 encoded as a quantum bit. We do nothing to it. We then make a measurement which extracts the classical bit. That classical bit value is, of course, 0. And here is our quantum circuit, which essentially does nothing. For a random process, we need to do something. So let's put a little gap in the middle of the circuit there, and then we can draw a box, and that box is going to contain an operation called a Hadamard, and we denote a Hadamard with an H. And with the Hadamard, the probability is 50-50 whether it's going to come out as a 0 or a 1. So we can use a little histogram perhaps to show that the probability of a 0 or a 1 is equal at 0.5. So then this is very much similar to the process of a coin flip, where we have outputs of 0 and 1 and an initial state of 0 and probabilities of half and half, at least for a single Hadamard. Now I'm going to wave a magic wand and make a few changes. Get rid of the probability tree. Now we have a circuit with two Hadamards. Remember that a circuit with just a single Hadamard gave us this histogram representing a random 0 or 1 as an output. Now that's what we would expect again if this was a classical random process, but this is not a classical random process and we don't get a 50-50 out of this. You can try it yourself in the IBM Quantum Experience or using Qiskit, and what you will find is that instead the output is 100% likely to come out as a 0. 0 goes in, 0 comes out. Similarly, if the input was a 1, which we can prepare by doing an XOR gate to flip this initial 0 to a 1, what we would find is that it would 100% come out as a 1. These two Hadamards seem to undo each other. Now there is a way to get our classical intuition back, and that is to insert another measurement gate in this gap here. Now rather than me slowly talking because I'm drawing at the same time, let's work a bit of magic. So here we have a more complicated circuit, but the first part here is exactly what we looked at earlier. An initial 0, a single Hadamard, a measurement, and the outcome is 50-50, 0 or 1. In the case that the measurement comes out as 0, it's the 0 state which gets fed into this next Hadamard and this next measurement, and in that case the answer would also come out 50-50, 0 or 1. In the case that this comes out a 1, exactly the same process, the Hadamard causes that to, with 50-50, output a 0 or 1 for the measurement. So overall, again, we have a 50-50, 0 or 1. It is exactly like two coin flips. We've just flipped our coin in a weird and quantum way. But in the case where we didn't observe it in the middle, where we allowed this quantum bit to not have a definite 0 or 1 state, but to remain undefined, we had a different result. It came out 100% exactly what we put in. The randomness was removed. And that is what we're going to have to dive into further. Let's go back to our probability trees. In the single Hadamard case, we started off with a 0 and we got either a 0 or a 1 as output. And these came with probabilities half and half. And so in the normal probability tree method, we would write down a probability of half here and a probability of half there. However, actually in these quantum processes, it's not probabilities that we need to keep track of, but probability amplitudes. So here we're going to have a probability amplitude of A0, and here we're going to have a probability amplitude of A1. And these amplitudes are, in this case, just the square root of the probabilities. In this case, they're both square root of half. And the probability of getting the output 0 is just the square of the corresponding amplitude A0. The probability of getting the output 1 is just the square of the corresponding amplitude A1. Now, in the case that we do not have an initial 0 here, but we instead have an initial 1, the probability amplitudes are slightly different. They are still the square roots of the corresponding probabilities, but instead of taking the positive root, we take the negative root, in this case, for the A1. So still we get the probability of the outcome 0 is a 0 squared, and therefore half. And still we get the probability that the outcome 1 is a 1 squared, and therefore half. But there was a minus sign in there. And that is going to become important when we look at two of these processes, one after the other. Okay, so here we've got our probability tree for two applications of a Hadamard using these probability amplitudes. We have an initial 0. Probability amplitude for the Hadamard creating a 0 is square root of half. The probability amplitude for outputting a 1 is also the square root of half. In the case that there is a 0, we just have that same process again. But in the case that we have a 1, we have an amplitude of square root of half here, but of minus the square root of half there. The way we get the amplitude for a whole branch in this process is again to just multiply together individual amplitudes, just as we multiplied together individual probabilities when we looked at the classical case. In the classical case, if we wanted to get the probability of this output of 1 via the process where we had a 0 in the middle, what we do is multiply together the probabilities exactly as we did earlier. In this case, if we want to get the amplitude for that process, then we multiply together the amplitudes. So let's do that. Firstly, there's an amplitude of square root of half, and then another amplitude of square root of half. So in the end, we get square root of half times square root of half equals half. And that's the amplitude there. Now, if we look at the amplitude for the other way of getting an output of 1, then we initially have the square root of half, and then we have minus the square root of half. So multiply them together, and the square root of half times minus the square root of half is equal to minus half. Now, if we want to get the amplitude for the process of just getting an output of 1, no matter what happens in the middle, we add up those amplitudes. So in this case, half plus minus half is half minus half, of course, and equal to 0. Where, just to be clear, this half is from there, and the minus half is from there. So the entire amplitude of this process is 0. If we square that amplitude to get a probability, the probability is 0. If we were to instead do the amplitudes for the process which gives us an output of 0, then we find that this has an amplitude of half, and this process also has an amplitude of half. Half is 1. So the probability of getting a 0 is 1. Because we're doing it with amplitudes rather than probabilities, and because those amplitudes are allowed to be negative, we can get these interference effects. And that allows the results to be a bit different than what we expect. Now you may be wondering, when are we supposed to work with amplitudes and when are we supposed to square them to become probabilities? And the point at which we square the amplitudes to become probabilities is exactly the point at which we have a measurement gate in our quantum circuits. It's that same process, which means that we have to stop working with amplitudes because we're not being quantum anymore, and have to start working with probabilities because we're becoming classical. So when we put a measurement gate in the middle and actually take these outputs, then it means that it no longer really makes sense to talk about the amplitude of this whole process, but we have to talk about the individual amplitudes of going from the initial state to the middle state, from the middle state to the final state. And that means that basically we don't have the opportunity for any interference effects, and that's why we see the same result as the classical case. So there you go, you've seen your first quantum interference effect. Interference effects are key to how quantum computing is unique, and we'll be seeing a lot more of them throughout this course. But this is a simple example, just to give you the taste, and one that you can easily reproduce either using the IBM Quantum Experience or using Qiskit. So give it a go. Do your first quantum interference effect, and that's basically half of quantum computing. Anyway, that's all for this video.